The last video we discussed two important problems in supply chain flows, namely information and money. Today we are going to consider a far more complex flow, namely the material flow across the supply chain. Now in supply chain we have a famous punchline. Supply chain is supposed to replace inventory with information. It's easier said than done. In spite of all the advances in information technology, in spite of all the advances in electronic payments, material flow still remains the Achilles heel of supply chains. Now consider the same dairy supply chain example. What do you think would happen if the farmer is not able to deliver the milk to the retailer because of a transport strike? Or what do you think would happen if his cows suddenly start giving only 50% of the milk they normally give? What do you think would happen if all the milk reaches the retailer but there is a retailer strike, as a result of which much of the milk gets spoiled in the stores? All this is an example of material disruption. How do you think we could handle material disruptions? There are three methods of doing it. Method number one, we need to maintain a safety stock and a decoupling stock, meaning each player of the supply chain has a certain minimum stock which offsets the variation in material flow across the supply chain due to differing capacities of different players to handle differing amounts of material. The second method of dealing with this is to have a proper and an accurate forecasting method. While this is easier said than done because most players have no clue as to the demand pattern of his customer. The third method is to use a pull system that Toyota called the Kanban. Kanban is a lovely method to eliminate variations in demand patterns, but apart from Toyota and a few other companies, very few have successfully implemented the Kanban pull production. So there must be some other method where we could achieve the same material consistency in flow. This is where we bring in Goldratt again. Goldratt proposed a lovely method known as replenishment. In his replenishment, he created a method that is both self-regulating and requires very little computation. Also, if every player in the supply chain follows the replenishment model, there's very little communication that they need from the other players to be able to function and manage their material stocks. Now, Goldratt proposed three rules in his replenishment policy. Rule number one is the ordering policy. In the ordering policy, it's extremely simple. Let us say you have the same players in the dairy supply chain. Now, let us assume the retailer is ordering for 100 liters of milk to the dairy farmer. Today, the dairy farmer supplies 100 liters of milk. So, tomorrow he should milk only 100 liters. Anything extra is not done here. On day 2, the farmer milks 100 liters of milk, but the retailer asks only for 80 liters of milk. What happens? The farmer has a stock of 20 liters of milk. So on day 3, supposing the retailer asks for 110 liters of milk, the farmer already has how many? 20 liters. So he is going to milk only as much as he has supplied on day 1. Simple, isn't it? Now, when the farmer is milking only as much as he supplies to the customer, there is going to be a certain mismatch in the supply given to the customer. This is maintained by the second rule. Now, what characterizes the ordering policy is frequent ordering, preferably every single day. There are certain people who order every 3 hours or even every hour. The faster the ordering is done, the more accurate is going to be the material flow across the system. So put it in simple words, whatever goes out is the same amount that a player orders from his supplier. Now, what happens if there is a variation in demand? This will definitely mean that the supplier has to make up for the difference in the stock. For example, today the customer orders for 100 liters of milk. So, the farmer tomorrow milks exactly 100 liters of milk. What happens if the next day the customer orders for 120? 20 liters less. Now, how do you make up for this? This is where Goldratt gave his second rule, the rule of maintaining a buffer. This is probably the easiest computation of buffer across so many inventory models available across the operations management spectrum. The buffer is meant to absorb variations in demand from the customer side. These variations are impossible to predict because they are highly random, unless both the customer and the supplier decide to have a certain standard variation. This doesn't happen. Goldratt's buffer is computed using three variables: F, L and D. F stands for the ordering frequency, L stands for the lead time and D stands for the demand. Now, the formula is the demand multiplied by the sum of the lead time and the ordering frequency. Now, ordering frequency could be every day, it could be every month, or it could be once in 3 months, but here we maintain a steady ordering frequency. We don't order in irregular intervals. The lead time should be as low as possible, but what happens when you have a variable lead time? We assume that the largest lead time is used in this formula to compute the buffer size. The same goes for the demand. The largest demand goes into this formula. When the demand is steady and the lead time is steady, it's extremely simple to predict the buffer size. Here too, we have simplified the entire process by using the largest lead time or the largest demand. Now we come to rule number 3, buffer resizing. A buffer is fine, but are we having the right buffer size? Is it too big? Is it too small? Here's where Goldratt gave his third rule of zones of a buffer. He divided the buffer into 3 zones: the green, the yellow and the red. Now, these 3 do not require complicated mathematics. Just take the buffer and divide it into 3 equal parts. Each part from the top to the bottom follow the order of green, yellow and red. Buffer resizing is done once in 60 days. If you resize very often, everybody gets confused in the supply chain. Now, at the end of 60 days, if a bulk of the stock has been in the green zone, meaning the top part, it means your buffer is too big. If a bulk of your buffer is in the red zone, it means your buffer is too small. It needs resizing. Goldratt gave a very simple rule. If your buffer is too big, reduce it by 33%. If your buffer is too small, increase it by 33%. However, we can follow a slightly more scientific methodology and find out what's the lead time and what's the demand. After all, buffer size is determined by these two, changes in lead time and changes in demand. So, over the 60 days, if you find out the peak lead time and peak demand and resize a buffer, presto, you have the right buffer size. Now, here is an exercise for all of you. Assume you have a department store next to your house and you pass on information. At certain times, he is out of stock. He is not able to supply the materials you want, say a bar of soap or maybe some rice or some other provisions. How would you suggest that he maintain stock to supply whatever you want whenever you want it? How do you think the information you pass should be recorded by him so that he doesn't get any miscommunication or he doesn't forget? How do you think he should standardize the payments you make to him? Use the principles you have learned to come up with an answer.